Now we're talking about equilibrium, and equilibrium is actually the reason why we need this idea of torque. So what does equilibrium mean? You've seen the concept before at the beginning of chapter 5, where equilibrium basically meant no acceleration. And of course, since net force causes acceleration, in a situation where there's no acceleration, there is no acceleration because there is no net force. Or, other way around, if you know that the net force on an object is zero, then you automatically know that it will not accelerate. Similarly, when we say no acceleration, we mean not only there's 0 meters per second acceleration, but there's also 0 angular acceleration. That is, if an object is rotating, it's rotating at a constant rotational speed, at a constant rotational velocity. As it spins, it's not spinning faster and faster as time goes by. It's not spinning slower and slower as time goes by. Or, if it's not rotating at all, it remains not rotating. In that case, it has a constant rotational velocity of 0. But constant rotational velocity is the important part, right? Constant angular velocity means no angular acceleration, just as constant meters per second velocity means no meters per second kind of acceleration. And of course, torques are the things that cause angular acceleration. So if there is no angular acceleration, then you know that there is no angular acceleration because the net torque on the object is 0. So there are really two conditions for equilibrium. If you observe that an object is in equilibrium, you know two things right off the bat. Net force is 0, net torque is 0. And then a reminder from last time, here's our equation for the magnitude of a torque. It's a product of the magnitude of a force and then the magnitude of a displacement, and then sine of an angle. The displacement is just the displacement from a reference point. You're free to choose the reference point anywhere you like, but usually we choose it at the axis of rotation. The displacement is a displacement from the reference point to wherever that force is acting, whatever point that force is acting on. And then the angle is the angle between the displacement direction and the force direction. Now that tells us only the magnitude of the torque. Torque is a vector, so it has a direction. Usually, in these cases, we're considering only torques in two possible directions, positive and negative, just as we've been considering angular velocities and angular accelerations only in two possible directions, call one positive, call one negative. And so how do we define positive or negative among torques? Well, it depends on how that torque changes the rotational state. And the important thing to remember here is that we call clockwise rotations negative and counterclockwise rotations positive. So for example, here's just a little some long rod, and we imagine this is the reference point. Maybe this point is nailed down, and if you push the rod one way or the other, the rod rotates about this fixed point. So if you were to push the rod this way, apply the force right here. So there's the force, and then there's the displacement vector that takes you from the reference point to the point where the force is applied. if this force starts pushing, it causes a torque. And torque changes the rotational state. In this case, the rod's rotational state changes from no rotations to, well, push it this way and it starts to rotate counterclockwise. Counterclockwise with respect to this reference point. And so counterclockwise rotation is being added. Counterclockwise rotation we call positive angular velocity. So positive angular velocity is being added. And a torque that does that we call a positive torque. Just in just the same way that if a force results in giving something more positive velocity than it had before, we say it's a positive torque. And now, imagine the other situation, reference point in the same place, and the force pushes the other way. Now it's pushing down and to the right, so it changes the rotational state of the rod from no rotation to clockwise rotations. Clockwise rotation we call a negative rotational velocity. So the rotational velocity of this rod has gone from 0 to something negative. Negative velocity, negative rotational velocity has been added, and any torque that does that, we call it a negative torque. Now, just for completeness, let's imagine putting the reference point here at the other end of the rod, the right end instead of the left end. And now imagine rotations with respect to the reference point. And we always think of the reference point as, say, a fixed point about which there could be rotations. So in this case, now if you push with a force this way, and then here's the displacement vector, that will make excuse me, that will make the rod start to rotate clockwise. The rotational velocity has changed from 0 to clockwise. Clockwise means a negative rotational velocity. So the rotational velocity goes from 0 to negative. Negative rotational velocity has been added onto this rod, and the kind of torque that does that is a negative torque. And then here, if you push this way, down and to the right, same kind of force as this, it'll make the rod start to rotate counterclockwise. Clockwise rotation we call a positive rotational velocity, or a positive angular velocity. So the velocity, angular velocity of the rod has changed from 0 to something positive. Positive angular velocity has been added on, and any torque that does that we call a positive torque. Now let's look at a few examples of how we can use equilibrium ideas to figure out various things. Usually we want to figure out the magnitudes of forces, or sometimes we might use torques in equilibrium to figure out distances or locations of various things. Since we're talking about net torques, whenever we're talking about an equilibrium situation, we have to add up the torques correctly in order to get the correct net torque. That's why we have to pay attention to which torques are positive and which torques are negative. Just as you have to pay attention to which forces are positive and which forces are negative in order to correctly write down the correct expression for a net force. If you don't, your answers will be wrong. So here's a simple example of a situation that's in equilibrium, but in this situation we only need to think about torques, won't need to think about forces. So imagine two little kids on a seesaw, and imagine that the seesaw is balanced. So one kid out here, and the mass of that kid, let's say, is 30 kilograms. Mass of the kid on the right is 30 kilograms. And we'll say that that kid is 1.2 meters away from the pivot point, away from the fulcrum right here at the middle where the seesaw balances. And that's the point that the seesaw will rotate about when it's seeing and sawing. And then the other little kid is at some unknown distance away from the balance point, and we're trying to figure out what that distance is. So we'll call that distance x, and there's the other kid, and the mass of the kid on the left is 25 kilograms. Now you know from you might know from just everyday experience that in order to get balance, and the less massive thing is going to have to be a little bit farther away than the more massive thing. That's because of the way torques operate. So, in doing a question like this, we start the same way that we've started any previous problem involving forces. First, draw a picture that shows all the forces, and now in this case, it's important to show also the point where the forces act. You know, the point on the object of interest where the forces are acting. In this case, the object of interest is the board, the seesaw, and the different forces produce different torques because they're acting on different points. So there's the board, and then right in the middle, there are two forces. The only upward force on the seesaw is a normal force that comes from this surface here at the tip of the base. And then all the other forces, there are three other forces on the seesaw, and they're all downward forces. One force is, of course, the weight of the seesaw itself. And you read previously about situations where you have an extended object. There's mass extended over a whole volume, which means there's a little gravitational force, a little weight force acting on every point in that extended object. A little weight force acting at every point in the volume of that object because there's a little bit of mass everywhere in the volume of that object. So there's a huge number, divide that board into a million little bits, and then there's a million little weight forces. But we have this concept called center of gravity. We can imagine that the effect of those millions and millions of little weight forces, each acting on a different point, is the same as the total weight of the whole object pulling on just one point, and that point we call the center of gravity. It's easiest to think of the center of gravity as sort of the average location of all the mass, because when you look at it that way, you realize that if mass is evenly distributed along the whole volume of the object, right, same amount of mass on the left side as there is on the right side, then the average location of mass would be right in the center. And there's no reason to think that the mass in this board isn't evenly distributed. So if it is evenly distributed, then the center of gravity, the average location of mass, is right in the middle. And at that point, that's the center of gravity. So you can imagine the entire net weight of the object is one force, only one force, pulling on the center of gravity. You can think of just one weight force on the board, and it's pulling on the center of gravity. And of course, the weight of the board is just the mass of the board times g, 9.8. Then there are two other forces. There's a force from the kid on the right and a force from the kid on the left. Those are normal forces. As the kid, think of the kid's rear end as a surface pushing down on this point on the seesaw board. A surface that pushes, that's a normal force. Normal force from the kid on the right. And likewise here, a normal force from the kid on the left. But we know something about those normal forces. Think for a minute about the kid on the right. The kid on the right, if the whole seesaw is in equilibrium, then the kid on the right is in equilibrium too. Right? The net force on that kid is 0. But what are the forces on that kid? There's the kid's weight, the kid's mass times g, 30 kilograms times g, and then there's a normal force from the seesaw pushing up on the kid. Normal force from the seesaw on the kid sitting on the right. This force here is a normal force, I had this backwards. This is a normal force on the kid on the right, seesaw pushing up on the kid on the right. This is a force from the kid on the right pushing on the seesaw. This is a force on the seesaw. This is a force from the seesaw on the kid. Now, the kid is in equilibrium, so that means these two forces cancel out. The normal force from the seesaw on the kid on the right is equal to this force, the kid on the right's mass. But also compare this force and this force. They are a third law pair. You need to be able to recognize third law pairs when you see them. How do we know they're a third law pair? They fit the pattern for a third law pair. Remember, in a third law pair, both forces are the same type. They're both normal forces. They're in opposite directions. This one pushes up, this one pushes down. And both forces describe an interaction between two and only two things. Seesaw and the kid on the right. Seesaw, kid on the right. And in a third law pair of forces, the source of one force, the kid on the right is the source of this force, becomes the thing that feels the other force. And the thing that feels one force, right, the seesaw feels this force, becomes the source of the other force. Source and receiver have their roles flipped around when you go from one force to its partner force. So these two things look like a third law pair. They act like a third law pair. They fit the pattern for a third law pair, so they are a third law pair, which means this is just as strong as this. These two forces have equal strength, equal magnitude, but the magnitude of this force was equal to the weight of the kid on the right. So since this is equal to this, the magnitude of this is also equal to the weight of the kid on the right. And similarly, you could go through exactly the same argument for this one. the normal force here on the left, the normal force from the kid on the left on the seesaw is equal to the weight of the kid on the left. Mass of the kid on the left times g. So now now that we know that, let me just redraw this diagram to indicate that fact that we now know. So the forces on the board are the weight of the board pulling on the center of gravity, and then the normal force from the support pushing up on the board, and then a force from the kid on the right pushing down on the board. That force is really a normal force, but it's equal to the weight of that kid. And then a normal force from the kid on the left, which is equal to the weight of the kid on the left. And remember, what we're trying to find is this distance here. We know that this distance is 1.2 meters. So let's do it. What do we do next? Well, we do some stuff that we've already known that we should do, and then some other stuff that's very similar. The thing we know to do is just write down how the net force comes about, how the forces that we've identified add together to give you the net force. And it's equilibrium, so the net force is 0. And the net force is always all the force in the positive direction minus all the force in the negative direction. We'll just say positive is up and down is negative. So all the force in the positive direction is just this normal force. All the force in the negative direction is the other three forces. The normal force from the kid on the left, the mass or the weight of the board itself, and then the normal force from the kid on the right. Now, we could do the same kind of thing with torques. We know that the net torque is 0, as well as net force is 0, because this is in equilibrium. We can write down a similar expression showing how all the torques combine to give you a net torque which will be equal to 0. But to do that, we really need to first find a specific expression for each torque. Go back to the basic equation for torque and then do that. Magnitude of torque is magnitude of force, magnitude of displacement, sine of the angle between force direction and displacement direction. This is a displacement from a reference point to where the force is acting, so we have to choose a reference point first. The best reference point, the one that usually makes most sense, is the axis of rotations. And if the seesaw were rotating, it would rotate right about the pivot point here. So let's call that the reference point. Right there. And now, figure out the torques. Each force could produce some kind of a torque. What about the torque from the normal force, from this force right here? That's 0, because the displacement is always displacement from the reference point to the point where the force is applied. Here's the reference point, but this is also the point where this force is applied. So the distance between the reference point and the point where this force is applied is zero distance. Right? The magnitude of the displacement for the torque caused by this is zero. Likewise, the torque caused by the weight of the board is also zero because that force is being applied right on the reference point. The center of gravity, where this weight force pulls, is also the reference point. So the distance from the reference point to the point where this force is being applied is again zero distance. The magnitude of the displacement vector for this force is again zero, and again zero displacement means zero torque. Just like you saw last time when I was looking at those examples of torques on a door that you're trying to open. If you apply the force right on the reference point, you get no torque at all. So the only two non-zero torques will come from those two forces. The torque from the kid on the left, first term is magnitude of the force. The force is the normal force from the kid on the left pushing down on the board, but the magnitude of that force is just the kid's weight, mass of the kid times g, or mass of that kid was 25 kilograms times g. You'll worry about multiplying by g later. Next term is the magnitude of the displacement. The displacement takes you from the reference point to the point where the force is applied. So a displacement vector that goes from here to here is the displacement for that particular torque, and that displacement vector will have a magnitude of x meters. Notice we don't have all the numbers to get a number for this torque, so we write it as an algebraic expression. And then the third factor is sine of the angle between the displacement vector and the force vector. Displacement points this way, horizontally straight to the left. Force points straight down, so the angle between the displacement direction and the force direction is 90 degrees. They're perpendicular. Sine of 90 degrees turns out to be just plain 1. So that's the magnitude. And furthermore, that torque is going to be a positive torque. (25 kilograms gx). It's a positive torque because if things got out of balance and the seesaw did start to rotate because of the torque from this force, pushed down on this side, there would be counterclockwise rotations with respect to the reference point. Counterclockwise rotation is a positive rotational velocity, and a torque that makes positive rotational velocities appear that's our definition of a positive torque. Now the torque due to this force looks very similar. The torque due to the normal force from the kid on the right, the first factor is just the magnitude of that force, which is equal to the weight of the kid on the right, 30 kilograms times g. And then the next factor is the magnitude of the displacement vector for this torque. Displacement points from the axis of rotation to the point where the force is applied. So this distance is the magnitude of that displacement, 1.2 meters. And again, the last factor is sine. It's sine of, again, 90 degrees. The displacement vector points from here to here, so it's horizontal. The force is again vertical, so the angle between displacement vector and force vector is 90 degrees. Sine of 90 degrees is once again 1. So there's the magnitude of this torque, and this torque is a negative torque because it causes negative angular velocity to appear. If things were out of balance and a push here, the torque here were to make things rotate, it would make things rotate clockwise about the reference point. Clockwise rotation is a negative angular velocity, and if a torque makes new negative velocity appear, we call it a negative torque. So now we do what I was talking about earlier. We write down the expression that shows how torques combine to give you the net torque, just as we've been writing down expressions that show how forces combine to give you the net force. So the net torque, which is 0 because this whole system is in equilibrium, is just the sum of those two torques that were not 0. The torque from the kid on the left is a positive torque equal to 25 kilograms times g, the kid's weight, times x meters, the magnitude of the displacement vector for that torque. And then the second torque was that one, minus 30 kilograms g times 1.2 meters. And that all adds up to 0. So there's a factor of g, 9.8 meters per second in both terms on one side of that equation. So if we divide the whole equation by g, the g disappears. It's a common factor for every non-zero term in the equation. So that's why I didn't multiply everything by g earlier. We don't have to, because all the g's just cancel out. So then what we're left with is 25 kilograms times x minus 30 kilograms times 1.2 meters equals 0. Or x equals 30 divided by 25. Just divide both sides of just divide the whole equation. Well, add 30 times 1.2 to both sides of the equation, and then divide the whole equation by 25. So that's x, and then when you do the math, it comes out to 1.45 meters. Since we had only two significant digits in the numbers that we put into our calculations, we're really only allowed 2 significant digits in our answer. So we should say that, strictly speaking, we have to say our answer is rounded off here, 1.5 meters. But the idea is that this is just what we expected. The smaller mass, the smaller kid, had to be farther from the balance point than the big kid in order to make things balance. And that's because when you're balancing things, putting things in equilibrium, you have to balance the torques. And in this case, the force was larger, and in this case, the force was smaller. Torque is a force times a distance. So if this force is larger, this force is smaller, then this distance has to be larger than this distance in order to make the two torques, the force times the distance, balance out. Now, if you want to take a break, just stop the video right here for a minute. I've got one more example to show after this one. Similar to the last one, just a little bit more complicated. Let's imagine a big board that is 4 meters long, and it's supported by concrete blocks on the two ends. and the board has some mass. It's 20 kilograms. And there's some guy here sitting or standing at that point on the board, 3 meters from the left, 1 meter from the right. And the mass of that person is 80 kilograms. And I would obviously, there's an upward normal force from this block pushing up on the left end of the board. There's an upward normal force from the right-hand block pushing up on the right-hand block. I would like to know the magnitudes of those two forces. And you can figure those numbers out by using equilibrium ideas. But you begin the same way as always. Draw a diagram that shows what the forces are and where on the board those forces are acting. In this case, we have 4 forces. There's a normal force from the left-hand block pushing up, and a normal force from the right-hand block pushing up. And then there's the weight of the board itself, which will be pulling on the center of gravity. And again, the reasonable assumption to make is that the mass of the board is evenly distributed, so that the average location of mass is right in the middle. Average location of mass is just another name for another way of thinking about center of gravity. So center of gravity is right here in the middle, and so the weight of the whole board we can think of as just pulling on that one point. And then weight is just mass times g. Mass of the board times g. 20 kilograms times g in this case. And then the fourth force is a normal force from the person over here, the soles of their shoes, pushing down on the board. But of course, just like in the seesaw example, that normal force from the person pushing down on the board is just going to be have the same magnitude as that person's weight. So a normal force from the person on the board, but the magnitude of that force happens to be the same as the person's weight. Mass of the person times g. Those are the forces, and we can write down the expression that shows how they combine in order to give you a net force. And since it's in equilibrium, we know that net force is 0. Again, we'll say up is the positive and down is the negative direction. So the net force is just all the force in the positive direction. That's the 2 normal forces from the 2 blocks at the ends, NL plus NR. And then the 2 downward forces are the weight of the board and the normal force from the person pushing down on the board. That force happens to have the same magnitude as the person's weight. So I'll write it as mass of the person, g. And the board is in equilibrium, so the net force comes out 0. All the upward force completely cancels out all the downward force. Now we'll do the same thing that we did in the previous example. Figure out what the torque is for each force, and then write down the expression that shows how those torques combine to give you a net torque, which will be 0 because this is equilibrium. So to do torques, first you have to choose a reference point. In this case, you can be a little bit clever in choosing the reference point. Notice that we have 2 unknown quantities. So this and this. So things will be easier for us if we get an equation that has only one of those unknowns in it. And we can do that by putting the reference point at the point where one of the unknown forces acts, because let's put the reference point there. We've seen that any force acting right at the reference point gives you 0 torque. So the torque due to this is 0, and the result of that is that this unknown term here will not appear in our net torque equation. The only unknown that we're going to have in our net torque equation is this one, so it'll be easy to solve for the value of NR. So, torques, what do they look like? I just said that the torque due to the normal force from the brick on the right is 0, because that force NL, normal force on the left, that's 0 because NL is acting right on the reference point. Torque due to the weight of the board is just, well, remember the first factor is the force, the weight, which is mass times G, 20 kilograms times 9.8 meters per second squared, times the magnitude of the displacement vector, which in this case takes us from the reference point to this point here, which is right in the middle of the board. The whole board is 4 meters long, so this distance, the magnitude of the reference point is, or the magnitude of the displacement vector is 2 meters. And then the third factor is sine of the angle between displacement and force. Now, just like in the previous problem, displacement is horizontal, force is vertical, they're perpendicular. So the angle between horizontal displacement and vertical force is 90 degrees. Sine of 90 degrees is plain old 1. So there's the magnitude of the torque due to this force. And what's the sine of that torque? If a push here started to cause rotations, and we always think about those rotations as rotations with respect to the reference point, those rotations with respect to this point would go like this. They'd be clockwise, and as we've seen before, that's negative torque. Clockwise rotations are negative angular velocities. So a push here must give a negative torque, because negative torques make negative angular velocities appear. Then the torque due to the force from the person pushing down on the board. The first factor in the torque equation is the magnitude of the force, which is equal to that person's weight, mass times G, which is 80 kilograms times G 9.8 meters per second, times the magnitude of the displacement vector. Displacement vector takes us from the reference point to the place where the force is applied. From here to here is 3/4 of the way along this 4-meter board. Remember, this was 1 meter, so this distance is 3 meters. And that too is a negative torque. Because just like this push, a downward push right here would make clockwise rotations appear, clockwise with respect to the reference point over here on the left. Clockwise rotation is negative angular velocity. So the torque from this force would be causing negative angular velocity to appear. That means it's a negative torque. Then finally, the last torque, this one, that'll be positive torque, but we don't know the number, we don't know the numerical value for that force, so we can't get a number for that torque the way we could for these other two. So we write it as an algebraic expression. There's a powerful tendency to want to put in numbers even when you don't know the value of the numbers. So try slow down and try to avoid that temptation. The torque due to that force is just equal to the magnitude of that force, whatever it is. We don't know, so we'll just give it a variable name, times the magnitude of the displacement vector. Displacement vector takes us from the reference point to where the force is acting. That's the whole length of the board, 4 meters. And just like in every other case, the displacement is horizontal and the force is vertical. So the angle between displacement and force is 90 degrees, and sine of 90 degrees is 1. So the last factor in this equation is 1. So that's it for the magnitude. And that torque is a positive torque because if a push over here were able to make rotations appear, it would make counterclockwise rotations appear, counterclockwise with respect to the reference point. Counterclockwise rotation is a positive angular velocity, and if a torque makes positive angular velocity appear, we call it a positive torque. So now we can write down an expression that shows how the torques combine to give you the net torque, which is 0 because this is equilibrium. First, let's just get the numbers for these two torques. Where am I here? Okay, here, this torque, 20 times 9.8 times 2 times minus 1 is minus 392 what? Well, a torque is a force times a distance. Forces are in newtons, distances are in meters. So this is 392, a force times a distance, newton times meters. And then this 80 times 9.8 times 3 times minus 1, that'll be minus 2,352. Same thing, minus 2,352 Newton meters, because it's a force times a distance. And then that, we don't know what NR is. We're trying to find NR, so we just leave it like that. And now write down our expression that shows how torques combine to give you the net torque. Net torque, which is 0 because it's in equilibrium, equals the torque from this force, which was 0, plus these two torques, minus 392 Newton meters minus 2,352 Newton meters, plus that torque, plus force from the right times 4 meters. That's all equal to 0. So what we really have here is add 392 to both sides, add 2,352 to both sides, and then on the left side, then you now have 2,744 Newton meters equals NR times 4.0 meters. So that means NR, which you get just by dividing both sides of the equation by 4, is 686 newtons. And now once we know NR, we can figure out what NL is, the normal force from the support block on the left. And we can do that just by going back to an equation that we wrote down earlier. I erased it, but we wrote it down earlier. The equation that shows how forces combine to give you the net force, which will be 0. So let's rewrite that and then find what NL is. Net force, which is 0, is just NL plus NR, which we just figured out, 686 newtons. Minus the downward forces. One downward force was the weight of the board, which is mass of the board times G. That's 20 kilograms. That's 9.8. So 20 times 9.8 is 196 newtons. Notice one thing here. What goes here is a force. It's very, very easy to make a mistake and put in this slot where force should go. It's easy to mistakenly put this torque in this slot here where a force, not a torque, should go. Right? This is the torque caused by this force, but this is an equation for net force, so here you want a force, not a torque. You want just the magnitude of the force, the magnitude of the weight. And then minus the normal force from the person, which was equal to the person's weight. Mass of the person times G. This is 80 kilograms, this is 9.8. So that comes out to minus 784 newtons. And it all adds up to 0. So now you've got an equation that has only one unknown, NL. Again, notice what you want here is a force, not a torque, but it's very easy to make the mistake of putting in this torque number in this slot where you should have a force number, not a torque number. This is the torque caused by this force, but in this slot you want a force, not a torque, because this is the equation for net force. Anyway, do the arithmetic with that equation, and you will find that NL comes out to be about 294 newtons. So, notice one thing here. The upward force here was 294 newtons, and L was 294 newtons. The force over here, NR, was 686 newtons. That should make sense, because when you look at the total weight that these two forces are supporting, there's more weight over here on the left than there is on the right. Right? The person is 3/4 of the weight to the right. More weight over on the right side than on the left side, so you would expect it should kind of feel correct that the right hand support force has to be stronger than the left hand support force. All right, we will think more about this in class.